to continue on exponential growth and decay, our next application is half-life. And half-life is used in carbon dating and as well as in radioactive material decay. So it has a ton of interesting applications. And a half-life is defined as it's the time required for half of a radioactive substance to decay. So the applications that we're going to talk about are for nuclear material and carbon dating. How they tell how old something is when they find it fossils and such. So, in other words, for carbon dating, or for half-life, right? If you have 100 grams of a substance and the half-life is 50 years, then what that means is in 50 years, when you look at the substance, you will have 50 grams of the substance because half of it will have decayed away. In another 50 years, you will then have 25 grams of the substance. And in another 50 years, you'll have half of that, 12.5 grams of the substance. Okay, so it decays, and then it is a exponential decay function because the decay rate is fast, and then it does slow down. So actually, the equation is the same as what we've already been using for uninhibited growth and decay. A of t is equal to a naught times e to the kt. But we know that k will be less than 0 for decay. Okay. And so k is called the rate of decay still. All right, so let's take a look at a problem about carbon dating. Traces of burned wood along with ancient stone tools in an archaeological dig in Chile were found to contain approximately 1.67% of the original amount of carbon-14. Carbon-14 is a certain type of carbon that they use because they know how fast it decays. So they have literally observed it decay, and so they know the half-life of it, and so therefore they can tell based on how much is left in the object, they can tell when it was alive, or when it was alive, because carbon-14 is in organic material like plants and animals. All right, so it says if the half-life of carbon-14 is 5,730 years, approximately when was the tree cut and burned? And that's why we're looking at the tree, because that was an organic material. It was a living thing. All right, so for part A, our equation being A of t is equal to a naught e to the kt. Okay, the things that we do know are that the half-life, so in other words, this side is 1/2, okay, is 5,730 years. So if the initial amount is 1, the final amount at time t is 1/2. It's kind of opposite the doubling problems that we just did, right? Because this is half-life. E to the k, and then the t is the 5,730. So we are, instead of looking for the doubling rate, we're looking for the half-life or the half rate. Okay, so the process is the same though. We can take the natural log of a half and set that equal to k times 5,730. So we know that k is equal to the natural log of a half divided by 5,730. And, you can type that in. You do get a number with maybe some scientific notation. It's a pretty small number. But I'm going to leave it like this number for now. Okay. So now it says, when was the tree cut and burned? Okay, so we know that 1.67% of the original amount is left. So let's say A of t, right? Because we're looking for, now we're going to look for when. So I guess we don't actually want A of t, we actually know the amount left, right? So that's 1.67%. If you use a percent, you're going to want to say 0.0167. And that I'm going to write up here, 1.67% is the number 0.0167. Okay, so we can't use 1.67% in the problem. That's out of 100. All right, is equal to e to the, well, now we know k. So natural log of a half divided by 5730, and that's times t. Okay, so notice that there's a lot going on here, but we actually know all of the information of the problem except for t. So we're just solving for t, and since it's in the exponent, we're going to change to log form. So that's natural log of 0.0167 is equal to natural log of a half over 5730 times t. So t equals natural log 0.0167 divided by, put this in parentheses because all this stuff it's a lot, you know, natural log of a half over 5730. Oh, that looks super fun to type into my calculator. So let's try that now just to make sure we can all do it. Clear out this last problem. Natural log 0.0167. Let's end that parenthesis and divide. And then let's open a denominator parenthesis again. So natural log of a half, I'm just going to type 0.5, enter, and parenthesis there, divide by 5, did I hit a 5? 5730, end the denominator parenthesis, and hit enter. 33,830 years. 33,830. Okay, so in other words, this tree is about 33,000 or 34,000 years old. Okay, which that does kind of make sense. There's not that much carbon left, 1.67%. We know that the half-life is 5,700 years, so it should be quite a bit of years. Okay. Okay, so to graph this equation for part B, we really I'm going to write down the equation for us because I think we kind of didn't specifically write down A of t equals, and then that's just the e to the natural log of 0.5 over 5730 times t. Okay, so that was what we came up with for the equation because really all we really needed to know was that rate, right? The natural log of 0.5 over 5730. So when you graph that in your calculator, go to y equals, put in the equation e raised to, make sure everything is up in the exponent when you do it. It totally works. And then when you hit graph, my guess is that you're not going to see anything again. I guess I can see it. Actually, I see a little blue line being graphed. Remember that our x and y axes were from, probably the last problem. So we have to change those, the window. So go to window. The x is still the time, right? So I think it's fine to start the time at 0. But then we need to see at least 5,000 years, right? And really, if we want to see the whole thing that we've graphed, that was 33,000 years. So we might want to change it to like 35,000 for the x-max, okay? Now the y is also a little confusing. That's the amount. Okay, and we weren't actually given an actual amount. We were just given that 1.67% remained. Okay, and we used the value 0.0167. So the amount that we have is actually between 0 for y min and 1. Okay, 1 being all and 0 being none. So we want to set that to 0 and 1. All right, now when we hit graph, we definitely see a lovely decay graph. Very exciting. Okay. So we start with a full amount of 100% of our carbon, and it gets smaller and smaller. It is a horizontal asymptote. It never actually technically reaches 0, but it gets really, really close to 0. So if you draw this on your paper, you're going to want to label your axes 0 to 1 and 0 to 35,000, right? All right, and then it says use the graph to determine the time that elapses until half the carbon is left. So if half the carbon is left, that means go to the amount, the y equals, and graph a y2 of half, or 0.5, and hit enter. And that's going to tell us that time when half the carbon is left. I hope you already know the time when half the carbon's left, but let's just see. So we're going to intersect those. So second, calculate. Number 5 is intersect. And then remember, you're entering the first curve, enter the second curve, enter a bad guess, and it will give you the intersection. 5,730 years. Oh yeah, because that's the half-life. So we did it right. That is when half the amount of carbon is left.